Much of it is anatomy. So if necessary, I'm going to cover some of that anatomy in lab, okay? Starting with today, and I know today's Thursday, but anybody my Tuesday who wants to have a preview of what you guys are going to have on Tuesday, you are welcome to come today to Thursday. Any Tuesday folks planning on coming today? Just to hang out? Okay, I've also asked that endocrine slides show up today in case anybody wants to look at the endocrine slides. I've asked specifically to get those trays out, right? So kidney, most important part of the kidney is that functional unit called the nephron. We are going to spend time on that today because there are different things that will happen in a nephron. Urinary bladder and urethra, that's pretty straightforward. It's just pretty much anatomy from that point on, okay? The goals for the lecture, this I want you to add also as your study guide if you haven't been doing so already. And it's just a matter of not just identifying and answering the questions, but understanding the big picture rather than simply memorization of the answers. So with the kidneys, these are the functions. Filtering the blood, filtering fluids, getting rid of waste in something called excretion. When we talk about excretion, there is secretion with an S, and there's excretion. Excretion means it's something you want to get rid of. So any kind of waste product, we say that it's excreted. So when we say sweat excretes waste, that means that the waste is something that we are getting rid of. Before we end up producing urine that we want to excrete, we do have to have these processes that will alternate with each other in the repeating unit called the nephron. Okay? So, at the end, we want to excrete our waste. We're going to excrete urine. What exactly is in urine? Nitrogen-based waste. Nitrogen-based wastes. These are the following. They're all nitrogen-based. Urea, uric acid, creatinine. This is all from, as a consequence of nucleic acid and protein breakdown. This is why urine smells like ammonia. What is ammonia? It's as nitrogenous as you can get. Okay? It's nitrogen-based waste. Right? Also, what our kidneys will do, they're going to regulate blood volume and blood pressure. They're going to be involved in water balance, salt, and acid-base balance. So we're not going to go super deep into how they're involved in that because it's all physio. It can get very physio heavy, but we're not going to go physio heavy. We're going to go straight with anatomy, and I'm going to give you physio context as necessary. Okay? Where the kidneys are located, we consider them retroperitoneal. That means that they are not covered in peritoneum. They exist behind the peritoneum, and they are anchored to the wall. So with this one, I'm going to bring back to lab, okay? So those who are going to lab today, I am going to mention this and go over these slides. I'm going to go over this again on Tuesday, just so you have the anatomy of it. Everybody so far? All good? Okay. These are where we produce urine. This is where we collect urine. This I will also go over in lab anatomy as well, where we collect urine for us to take it into the ureter. This, though, I'm going to go over here. This, the blood vessels, there's a lot of red and there's a lot of blue. Don't let it scare you. You do not need to know this for lab, but you need to know it for lecture exam. By the way, the lecture final, semi-cumulative, the majority, about 75% of it is all new stuff. So if you feel stuck on the cumulative part thinking like, am I overstudying? Do not overstudy for the cumulative part because the majority of the points are going to come from the new stuff, which include digestive, urinary, and reproductive. All right, let's start with the renal artery. Renal artery we're fairly familiar with. The renal artery is going to take blood into the kidney, right? And it's going to break off into what's called the interlobar artery. Each of these repeating units, by the way, those are called lobes. So to be an interlobar artery, that means that you're going to be going between the lobes. So from the renal artery to the interlobar artery. Then from the interlobar arteries, you're going to notice that, or you should notice, because here's an interlobar artery, it's going to become an arch. And right now we're just paying attention to the red, even though the blue is there. Each of those arches, if you think of arch, each of those arches is what's called an arcuate artery, because it's an arch. From the arcuate artery, that's now going to kind of fan out, and they're going to radiate. And they're going to radiate into this area called the renal cortex. So what is the name of that artery that radiates into the renal cortex? The cortical radiate artery. Your textbook calls it something else. Now, if I told you what it calls it, hopefully you will prefer the cortical radiate artery. They call it everywhere else the interlobular artery. You have your interlobar artery and then you have your interlobular artery. Okay, which term would you prefer? Cortical radiate artery, because it radiates into the cortex. If you tell me interlobular though, that's okay too. If you prefer that one, that's fine. But I think this one's easier because it radiates into the cortex. And I'm going to zoom in from that cortical radiate artery and we're going to focus just on this part. I'm going to draw the beginning part of a nephron for you, and I'm going to erase this part because we don't need it anymore. I want you to pull out two colors, red and black. Actually, red and blue. Let's do red and blue. Because in the lab, I drew it on blue, so we're going to do blue. Okay? Draw the arrangement of these three very, very essential parts of the nephron. This, by the way, this little box over here, you need to know this for lab, that for sure. But I'm going to draw a picture for you so it makes sense, hopefully. I want you to draw a ball of capillaries. And then I want you to draw a large arteriole going in and a skinny arteriole going out. Draw arrows so they know what direction blood is going. This is called the afferent arteriole. This is called, I'm going to put a giant G that is right there, because that G is what's called the glomerulus. If this is the afferent arteriole, that's glomerulus. What is the only possible option for that one coming out? That's the efferent arteriole. Then I want you to take the blue marker or whatever other color that you have. Could be black, could be blue. I like to use blue in this case. And then I want you to draw another structure that is going to hug whatever ball of capillaries you made. And I want you to make something that looks like that. That is not a blood vessel. That is what's called glomerular capsule. This whole thing, by the way, take a third color, because now we're going to combine it all. This is called, oh dang it.
Happens with what's right here.
Okay, cool. It's okay. It's okay. This whole thing I put in a box. That whole thing that I put in a box, that's called the renal corpuscle. Blood is going to be flowing through anything that is red. filtrate is going to be flowing through whatever is in blue. So what do you mean by filtrate? Okay, I'm going to switch to my blue because we are blue associated here. I want you to go ahead and draw arrows going from that ball of capillaries into that space. Because what you're drawing with the arrows is a process, a very important process called filtration. Filtration, okay? So filtration. Filtration here. So that's taken care of. Okay, we went from the cortical radial artery, and the afferent arterial, to the glomerulus, to the efferent arterial, and then where that efferent arterial is going to end up going, it's going to end up going to what are called the peritubular capillaries and the vasa recta. These won't make sense yet until we draw the rest of the blue. So let's draw the rest of the blue, and I'm going to introduce right now the nephron, what the nephron is. So put down your red. I want you to make a squiggly passageway coming from that renal corpuscle. Then what we're going to do next, we are going to have a part of that passageway. It's going to go down like a U, and it's going to come back up. We're going to come down skinny. We're going to come up thicker. So copy how I do it. That's fine. Make a U. Make most of it skinny. And then come back up. And then make most of it thicker. You're going to draw another squiggle that looks like that, only that we're going in this direction. Let's do that. And this is very, very simplified form, okay? In reality, your kidney has about 1 million of these, and they're all crammed together. This is why when you look at the histology of the kidney today, when you see the histology of the kidney, it's all of this all crammed together because we have to fit about 500,000 in each kidney, okay? So last part, and this would have come from another nephron. There you go, okay? Let's draw some fluid flow. Just this one part is called the collecting duct. Everything else before that, that's what we call officially the nephron. And so, okay, we'll talk about what the peritubular capillaries and the vasa recta are. Peritubular capillaries are any of the capillaries that are going to surround the squiggly part here and the squiggly part there. Those are the peritubular capillaries. Those are capillaries that surround the tubule. We call this nephron a tubule, okay? A tubule. The vasa recta is the set of capillaries that is specific only to the loop. And then from there, the blood is going to go into the cortico-radial vein or the arcuate vein directly, into the interlobar vein, into the renal vein, and then finally back to the inferior vein cava. We're not going to spend a lot of time on what's going on in the peritubular capillaries and vasa recta. Just know their presence, that they are there. We will spend quite a bit on what's going on over here. So now we've got the nephron. This is the functional unit of the kidney. 4 plus 1. Filters fluids in 4 main steps. 1, 2, 3, and 4. Number 1 is the renal corpuscle. Number 2 is called the proximal convoluted tubule. Number 3 is called the nephron loop or the loop of Henle. 1 goes down, 1 comes up. Number 4, that is called the distal convoluted tubule. And then the filtrate, when we say the filtrate, the filtrate, the filtrate. Remember, blood does not travel through anything that is in blue. It does not. If it does, then your blood will end up in the urine. And as we know, blood in the urine is not something you want. Blood is supposed to stay in here. So what are we supposed to filter out? Plasma. That's really what we're doing. We are filtering plasma. So the two things you do not want in the urine are blood cells, one, and large proteins, because those are the two things that are not allowed to be passing from here. And anything that stays in here will end up as urine. So we got our collecting duct at the very end. This is going to be shared by many nephrons, and there's going to be something that will happen every single place. All right, so the anatomy of the nephron, we're okay with? Okay, the same picture is on the board in the next room. So, 3 processes in urine formation and where they happen. You know the 3 processes. Filtration only happens in one place. Step number 1 only. This that I'm drawing, that's filtration. Filtration really is, okay, when we are pulling all of the plasma, or a large amount of the plasma, with the exception of 2 things. What are the 2 things that are not allowed to pass through? The 2 things that you do not want in your urine. Blood and large protein. So everything else, that means amino acids, that means glucose, that means salts, that means water, all of that should be filtered first. And it's a bulk filtration. Bulk filtration, like blood plasma, but cell-free and low protein. Then you are going to alternate between what's called reabsorption and secretion. Reabsorption and secretion alternates depending on where we are. So some of it will happen in the PCT, some will happen in the loop, some will happen in the DCT. Mainly though, what we want is, we want a lot of reabsorption. Because whatever we pulled out from the blood, most of the stuff we pulled out and filtered, we actually need to put that back into the blood. Which is why, when we mention the peritubular capillaries and the vasa recta, that's pretty much where we're going to end up putting things back into the blood. That putting back into the blood is what's called reabsorption. We reclaim most of our nutrients, water, and essential ions. 99% of our original volume that we filtered has to go back. So when we say from tubular fluid to interstitial fluid, you can also put there /blood. Whatever ends up outside of this tubule is going to end up eventually in the blood. That's why. So let me draw some arrows of what's what. So reabsorption, big part that happens in the proximal convoluted tubule. Draw your arrows to demonstrate reabsorption so that we are leaving the tubule and we are going into the blood or the interstitial fluid. That is reabsorption. If it were secretion, which only happens in certain places, and secretion is not necessarily excretion. Secretion, whatever is secreted into the tubule and stays in the tubule, then we say it's going to be excreted. But secretion is the opposite from reabsorption. If we were to draw secretion, what would that look like? Where'd your arrows be? That's reabsorption. What is secretion? And I'm going to do it like later here. Where would you draw our arrows? From the blood and going in. That is secretion. Secretion, like I said, doesn't happen as frequently as reabsorption. Secretion is reserved for things that we actually want to get rid of permanently, but the majority of what we filter, we actually want to keep. But this is the stuff that we would reserve secretion for. Unwanted material, excess drugs, antibiotics, toxins, hydrogen ions. Those are things that we do not want to keep too much of. This is why urine is slightly acidic. Hydrogen ions is one of those that we want to regulate and get rid of. So that's why our urine is slightly acidic, because of the hydrogen ions that we secrete and then excrete. So that's from the direction of blood and interstitial fluid into the tubular fluid and eventually to be excreted as urine. Watch those 3 processes. Okay, so again, where's the one place filtration happens? Out of these 4. Filtration only happens in one place. What is that? Only at the very beginning. From here on out, we're going to alternate between reabsorption and secretion. Between the two, which are we going to see more of? Reabsorption or secretion? Reabsorption. This gives you a little bit more detail of what gets reabsorbed and where. I don't want you to memorize everything that is on this. But when you study, I want you to look at it and see if it makes sense to you. And that's usually what we have, like in the lecture. If I give you a slide and there's a whole bunch of stuff in it, it's not for the purpose of you memorizing every single thing in there. I want you to use what you already know, what you've identified, and go back to a complicated picture and see how it's all put together, okay? So, in this next part, it kind of goes into every single part. So we've got renal corpuscle, glomerulus, and glomerular capsule. The red and the blue. We have our fenestrated capillaries. We have afferent and efferent arterioles, which I talked about. Because this afferent arteriole, I wanted you to draw it wider than the efferent one for a very specific reason. Think of it as a hose. If you had a hose, and then you went ahead and you pinched the center of it, what can you tell me about the pressure of the water right at the point where you pinched? If you made it a little bit more narrow, it becomes a high pressure. So making your afferent one wider than your efferent one is very intentional, because that creates an extremely high pressure in that glomerulus. And it's that high pressure that is the driving force for filtration. If you didn't have a high pressure there, filtration is not going to happen. You're literally forcing plasma out. And so that's what it means by high resistance being in that area. The glomerular filtration rate is determined by the vessel diameter. So if you change the diameter of this afferent arteriole, that's also going to change the pressure and the rate at which filtration will happen. How many of you had caffeine today? Do you know how caffeine wants to make you pee? Because the caffeine allows for this afferent arteriole to be wide all the time, which means the rate of filtration is fast, which means the rate of urine formation is fast, which means your ability to go to the restroom is fast. That's the target of your caffeine, right there, right here. Okay? Pretty cool, huh? Now that you think about it. All right, so we've got the glomerulus, and then surrounding that we have the glomerular capsule. The glomerular capsule is the one that's in blue. You've got two layers, 1 and 2. One is visceral, one is parietal. Sound a little familiar? The one that hugs the glomerulus is the visceral part. The one that is away from the glomerulus is the parietal part. Then filtrate is captured in here, called the capsular space. That's the capsular space. Now we are in the PCT. Most important thing about that PCT, everybody, if you're going to capture it all in one line, most of your reabsorption happens here. That means 100% of your glucose and amino acids, it has to all go back into the blood. Let's think about, though, if you have untreated diabetes mellitus. What can you tell me about your blood glucose when you have diabetes? Your blood glucose is too high. The driving force for all the glucose to go back into the bloodstream is the proximal convoluted tubule. The driving force is the fact that it's going from an area where there is more glucose to where there's less glucose back in the blood. But if you have diabetes, your blood glucose is high, which means not 100% of the glucose ends up going back to the blood. What is the urine like from somebody who has unchecked diabetes? It has, what is in it? Glucose. Glucose is one of those that you're supposed to put back into the blood. But if you have diabetes, it ends up in the urine because not 100% of it goes back. And this is exactly where the problem is at the proximal convoluted tubule. So 100% of your glucose should go back. 100% of your amino acids should also go back. About 2/3 of your sodium and water have to go back. And what is it all going to be? Is that secretion or reabsorption? Reabsorption. Most of it happens in the proximal convoluted tubule. Now we are down in the loop. There is a descending and there is an ascending. This is where the physiology gets kind of crazy, but I'm not going to go super deep into it. I'm going to give you a generalized concept of the importance of this loop. Okay? All right. If we were to see where we are in the kidney, each of those parts of the kidney, which I didn't go over here, but we will go over a lot. Let's hear. Okay. What is the name of the outer part of the kidney? What was always the general name of the outer part of the kidney? Starts with a C. And then the inner part started with an M. What is the outside part? What do you think it is? It's a term that you've heard when you were looking at the adrenal gland. Only this time we're going to apply it to the kidney. What's the name of the section that is on the outside? The renal, starts with a C.
Cortex.
Mm-hmm. What's the middle? What if I told you that the nephrons are all clustered in the cortex and they extend into the middle? Because of the loop as part of the nephron, that allows for us to increase in osmolarity the deeper in we go to the medulla. Why is this important? The urine that you produce, do you make a lot of urine when you're going to the bathroom, relatively a lot, or is it very little? Okay, it feels like a lot sometimes. But over the course of the day, if you think about how much blood your kidneys actually filter, it's very little. Dilute or highly concentrated? Pretty concentrated, depending on your needs. If you drink a lot of water, it's going to be more dilute. But for the most part, it's highly concentrated. The loop, this loop allows for us to create a small amount of highly concentrated urine in the collecting duct. How do we get highly concentrated urine? Well, we need to have a driving force to force water out of that collecting duct and to go into the space. How do we create that? We make this space and the fluid in here super salty. That's why when I drew the arrow like this, increase in osmolarity from less salty to more salty, the deeper in you go. Why? We need to conserve water at the end of the day. So if you're a desert rat, okay, your collecting duct and your loop is super, super, super long. And the urine that comes out is actually semi-solid. That's how concentrated their urine is. Somebody asked me in my other class, is that painful? And I said, ask a desert rat. Okay? But we need to conserve water at the end of the day. So what we do here is really important. So we have to result in a higher ion concentration, deeper you go into the medulla. And by the way, this is what the vasa recta looks like. It's the purple ladder that surrounds it. I mentioned earlier the vasa recta are the blood vessels that are surrounding that loop. So to pull from this without really knowing or going into the physiology of how this works and how it happens, we are going to place transporters very strategically so that in the part that goes down, this is permeable to water and not to ions. The part that goes up, it's permeable to ions and not to water. So if you have a whole bunch of water leaving, okay, on that side, and then you have a bunch of salts leaving on that side. If you keep pulling so much water out, what is going to happen to the tubular fluid in the inside? More dilute or more concentrated? The more water you pull out. Super concentrated. So that now we get numbers that look like this. I don't want you to memorize the numbers, I want you to see the trend. what's happening? Let's pull out water. We started at what, 300? 300, by the way, is the osmolarity of your plasma. Pull out water, pull out water, pull out water. See how the number inside the tubule changes. All the way up to 1200. That is super concentrated. Then we go up. Is water allowed to move in the part that goes up? So in the descending part, water is allowed to move. Ions are not allowed to move. In the ascending part, ions are allowed to move. Water is not allowed to move. So what do you notice in your should you see water on this side? It's not permeable to water. What's allowed to move? NaCl, those are the ions. And so we pull out ions, ions, ions. Look what happened to our number. We went from 1200 to all the way down to 100. That is super dilute. What is the significance of that? Why are we doing that? We are making this environment super salty. And when we have this super salty, that's what's going to drive water to go into the salty environment. And at the collecting duct, this is also what's going to drive water to go into that salty environment. And that's the most important part of the nephron loop. Am I going to ask you an essay question on describing that? No. That's too much physiology, guys. Okay? Should you know what side is permeable to what? Yes, you do. Okay? All right. At the end over here, okay, so what I want to close out with for today, because there's the remaining parts here, okay, so you've got your distal convoluted tubule, and then you have the collecting ducts and the hormonal control, okay? This part I want to go over in lab since we didn't finish it, because I don't want to spend a lot of time on kidney anymore on Tuesday, because we need to reserve that for reproductive. That's our last shot. Okay, that's our official last lecture, all right? But I am going to leave you with this. You're not going to be coming to lab today, okay? Calculate. What is this amount? What do you think? Each one is a 2 big one. Calculate. How much volume do you see on the screen? If I said each of them is a 2-liter bottle, how much volume is captured on that screen?
90.
Give me a total. They're in boxes, multiply. How many liters is that?
180.
180 liters. What if I told you 180 liters is the amount of blood that both of your kidneys filter every single day? 180 liters of blood is the amount that both of your kidneys will filter every day. Do you produce 180 liters of urine a day? I hope not. If you did, you'd be running to the bathroom like 24 hours. That is how amazing your kidney is. We can take 180 liters of filtrate and whittle it down to about 1.5 liters per day of urine. That's how efficient it can be. So that's what that is. All right? Okay. I'm going to end for now because we are at time. The last part, again, I'm going to just finish this in lab and go over some of the anatomy and then just talk about distal convoluted, what goes on there, and then the collecting ducts. Okay? And then the rest of it, really, urinary bladder, ureter, and urethra, that's pretty simple. We have all anatomy.